if I was going to use substitution, what does it make sense to do here? Yeah, what for what? So let's call this equation A and this equation B. Any suggestions on how you want to substitute? Gotcha.
So we're trying to get to the other side.
Well, no, so when you substitute, you have some choices. And I would say I want to try and encourage you to go the easiest way possible. So this says 2x plus y is 6. You could rearrange that so it looks more like that one, but there's an easier way, I think. Yep.
Can't you like take the equation for y and like replace that y with that part of the equation?
Yep, so what you said is fine and you can use that method, but for this, since this expression stands for y, just take it and replace it there. So we're going to substitute this expression for the y that was sitting there. So 2x plus, now instead of y, use this expression because that stands for y. Negative 2x plus 2 equals 6. So there's equation A, but I've plopped this in place of y. But here's the crazy thing. When I clean up this side, what do I get?
2 equals
2 equals 6.
Oh, we learned this.
So what's that mean? 2 equals 6. Does 2 ever equal 6?
No.
No. So no solution. This was our good old parallel lines from the other side. But algebraically, if you work it out, that's what you're going to be looking at. So that system is inconsistent. There's no ordered pairs that would work in both of those equations. All right. So our last one here. Again, this expression is another name for y, so I'm going to take it and plop it into this first equation. So I'm going to have 6x plus 4. It's 4 times y, but now this expression takes the place of y. Negative 3 halves x plus 3. So there's my 6x plus 4y equals 12. So we've got to clean up the left-hand side. 6x plus. All right, who wants to do this lovely 4 times negative 3 halves? Negative 6, nice. Plus, so remember, you got to distribute negative 6x, don't forget our x there, plus 12 equals 12. Now if we clean up the left side here, what do I get?
12 equals 12.
12 equals 12. Well, that's kind of unusual too, but what does that mean? X is 1. Infinite? If that's 12. All right, 12 always equals 12, right? So, right, it could equal 1. Right. This is always true. So, infinite solutions. And once you work with this a little bit more, like you might even be able to recognize, oh, that's the same equation, it's just written in a different form. But if you don't notice it when you go through the algebra, you'll land at something like that. If it's a statement that's always true, then you were looking at the same line. I want to pause and ask other questions, but it's so different to run this, not so much like a regular class. Any questions, though? Feel pretty good? All right, so that was substitution and graphing. Yes, there's my question. Why would substitution method maybe be better than the graphing method? Not always, but maybe. All right, wait, what do you think?
It's quicker.
It's quicker? Do most of you feel like it's quicker?
Yeah.
Okay, what else? Great.
Unless you like write real big, you don't need as much space.
Okay, sure, it saves space.
If you don't have a graph, you have a way of doing it.
Okay, yep, if you don't have a graph available. And could you also imagine that for the sake of time, I made the lines intersect in a nice convenient point, but could you imagine there could be fractions and decimals involved? And when you're graphing, you wouldn't be as exact, but if you went through the algebra, you would get the exact answer. Okay, great. All right. Now I'm going to show you some applications of this stuff. Oh, no, we're not to the applications yet. I have to show you the third method. All right. So, here's our third method. And this is the one that you might have had teachers previewing with you a little bit, or you might have seen in the past. But this may turn out to be one of your favorite methods. Okay, but it's best used if your equations are written in standard form. So again, last week, standard form was mentioned to you. This is why it might be useful. For this particular method of solving systems, it's very convenient. So here I say we're going to make the coefficients of one of the variables the same for both equations. So it's sort of not really the same. I sort of think it's the same number but a different sign. So here, see how this says negative 4x? What if I wanted to turn this into a negative 4x? What would I have to multiply that whole equation by? If I multiply that by negative 2. But I'm not sure you're convinced that I'm allowed to do that, so let me ask you a question. Does 2 plus 3 equal 5?
Yes.
All right. If I double this whole side and double that whole side, is that still a true statement?
Yeah.
No.
Yeah.
Yeah. That's 4 plus 6 equaling 10, right? So long as I do it to the entire equation, I still have a true statement. So I'm going to multiply this top equation by negative 2. So that's going to give me negative 4x minus 2y equals 6. My second equation is still negative 4x. Oh, I didn't need the negative sign. So come back and just multiply that by 2 for a second and I'll show you why. We could have done what I just did, but it makes your life a little bit harder. If we just multiply it by 2, this next step is pretty quick. So I'm just going to double everything. So top equation is 4x plus 2y equals negative 6. Bottom equation is negative 4x plus 8y equals 16. So again, to remind you of something that you know, 1 plus 3 is 4, 2 plus 5 is 7. If I add up this side, what do I get? If I add up that side, what do I get? 11. Works with numbers here. We're going to do this over here with our equations. If I add these together, what do I get? 0. Then I get 10y equals 10. So y is 1. So if you can make one of the coefficients, when I said the same, I guess, again, you want them to have the same number but different signs, because then you can just add them together. One of your variables will drop off, which is where this gets its name from. It's going to be eliminated. We eliminated the x's, and we got that y is 1. Once you have that, we're going to have to plug y in to get what x is. So 2x plus 1 equals negative 3. So now I've got x equals negative 2. You also, if you want to be safe, you can take your y is 1, plug it into the second equation. Negative 4x plus 8 is 16. Negative 4x would be 8. So x is negative 2, means we did our math right. When we plug y is 1, x is negative 2 in both of those equations. So our solution is negative 2, 1. Now, I chose to get rid of the x variable the first time I went through it. I want to show you how you could have gotten rid of the y variable if you wanted to. And again, just to demonstrate to you that you can eliminate either variable, it's your call. I'm instead going to multiply the top equation. If I wanted to get rid of, the y has a coefficient of 8. So what do I need this coefficient to be? Negative 8, so that when I combine them it will go away. So I'm going to multiply the whole equation by negative 8. So that would give me negative 16x minus 8y equals 24. And I still have negative 4x plus 8y equals 16. Now when I put them together, the y's go away. Negative 20x equals 40. Look at that, x equals negative 2. It spits out the x value. So you can eliminate either variable. It's up to you, whichever one you see more easily. It's your call. But it's a pretty cool method.
Wait,
I think.
is this still like the graphing stuff?
Well, those would be two lines. We could graph them and see where they intersect.
Oh,
Yep.
okay. Wait, no, never mind. I thought this was a different problem. I thought I got lost.
Oh. Nope, same problem. I was just showing you could get rid of the other variable. All right. And again, this is going much faster than it ever would if we were teaching this unit to you. But I'm glad you're hanging in there. All right, turn to the next page. If you want. Well, one of my students, you know how much I love the pigs and chickens problem, so. But no more trial and error, no more guess and check, you're gonna solve this thing using a
Pigs and
system.
chickens problem is more business.